Hello everyone. This is part 2 of topic 8 and topic 9 for exam 4. Met it partway through topic 9 last time, where we were talking about the distinction between absolute and conditional convergence. So we saw an example where an alternating series converged after we made all of the terms positive. So we said, well, if making them all positive converge, then the original series should also converge. And we said that was intuitive, and that's actually a theorem. But we should also show that the converse is not true, where we saw an alternating series that if we made all terms positive actually diverged, but then by the alternating series test it converged. So we came up with the definitions for absolute and conditional convergence. And I just want you to note that on the table, which is your cheat sheet for the final exam, remember you can write anything you want on the back of this. It's posted in the handouts section of exam 4. They only have the first definition, number 1 here, which is if the sum of the absolute value converges, then the series converges. So that's the first definition. I'd like you to include this second definition as well, so you might want to put that on your cheat sheet. So that one is that if, and it's almost nice, it's got enough room here, if the sum of the absolute value of A sub n diverges, and then we said, but the sum of the A sub n converges, then the sum of the A sub n converges conditionally. So I would encourage you to add that to your statement. And remember, if the absolute value diverged, then the only way it can converge conditionally is by the sum of the A sub n converging is by the alternating series test. Okay, so you should make that note on your cheat sheet. And you can see I posted 2 cheat sheets. One does not have these formulas, and one does. So decide which one you want to use, or maybe you want to use the other one without these formulas at the bottom, and then just write them in smaller. But you're going to need those formulas for the final exam. So some examples. So the first thing we consider, you read the directions, you're going to be told absolute, conditional, or diverges. First thing you consider is the sum of the absolute value of A sub n. So that's the sum as n goes from 1 to infinity of absolute value -1 to the n plus 1th times 1 over n cubed. And what the absolute value allows us to do is basically just remove the alternating factor. So you could drop the absolute values, drop the alternating factor, and here we get the sum as n goes from 1 to infinity of 1 over n cubed. And then for this particular series, immediately you should recognize it as being a p-series, where p is 3. And if you have to check your table regarding convergence or divergence of a p-series, if p is greater than 1, the series converges. So then if you consider the definitions we just made, we took the absolute value, it converged. So it does fit the first definition where the absolute value converged. So then this converges. Oh, and I should have told you to add this here. absolutely. Okay, to that first statement. So therefore, immediately, we could say that by definition, that this series, I always like to rewrite the given series, you don't have to, but by definition, this converges absolutely. Okay, so next example, again, the first thing you do, take the sum of the absolute value of the a sub n. So that's the sum as n goes from 1 to infinity, absolute value, negative 1 to the nth, 1 over n squared plus 1. And what the absolute value allows us to do is essentially eliminate the alternating factor of, in this case, negative 1 to the nth. So we just get 1 over n squared plus 1. Now, in the last example, turned out to be simple because immediately it was a p-series and we knew its convergence or divergence. Here it's not as simple. This is resembling a p-series, but it's not exactly a p-series. So we actually have to pull out a comparison test. So here we need a comparison test. And you could use the limit comparison. I'm going to use the direct comparison test. Okay, so we'll call the sum as n goes from 1 to infinity of 1 over n squared plus 1, the given series, the sum of the a sub n, with regards to the direct comparison test. And we're going to compare it to, we call it the sum of the b sub n. In this case, just get rid of that extra little plus 1 that's in the denominator, and we get 1 over n squared. But then recall, we have to establish the term-by-term comparison between a sub n and b sub n. So we write down a sub n, we write down b sub n, literally their nth terms underneath. Which way does the inequality point? Well, denominator on the left is always bigger than the denominator on the right, so reciprocal would be less than. Remember, you could just plug a number in here for n, you get 1/2 if you plug in n is 1, and 1/2 would be less than 1 if you plug in is 1 there for b sub n. But then also recall that with the direct comparison test, the sense of the inequality tells you which test you're using. Under the comparison cluster, either I or II, and when a sub n is less than b sub n, it's case I. So this tells us case I, which is the convergent case. Okay, so let's go over here and I'll say now, what does the sum of the b sub n do? Well, that was the sum as n goes from 1 to infinity, 1 over n squared. It's a p series. P is equal to 2, which is greater than 1, and so it converges. Okay, so now there's a couple important things to note. You have to say by, let's say, the direct comparison test, the sum of the a sub n, which was the sum as n goes from 1 to infinity of 1 over n squared plus 1, also converges. So that was this sum of the a sub n. But notice that came by looking at the sum of the absolute value of the original alternating series. So therefore, by definition, the original alternating series converges absolutely. Because if the sum of the absolute value converges, then the series converges absolutely. But we had to pull out a comparison test to prove that the sum of the absolute value did in fact converge. Okay, so a couple more examples. Again, you start off, you read absolute conditional convergence. Maybe before we even start this one, let's say we'll rewrite it as the sum as n goes from 1 to infinity, negative 1 to the n plus 1th, 1 over, that'd be n to the 2/3, remember, power over root. Okay, and then we take the sum of the absolute value of the a sub n. So the sum goes from 1 to infinity, absolute value, negative 1 to the n plus 1th, 1 over n to the 2/3. Absolute value allows us to drop the alternating factors, so that just the sum is n and the absolute values as n goes from 1 to infinity, 1 over n to the 2/3. Okay, you should recognize that as a p-series with p equaling 2/3, and when p is less than or equal to 1, then it diverges. And again, if you have to go to your table regarding the p-series divergence, here it is, p is less than or equal to 1, it diverges. Okay, so this series has no chance of converging absolutely, but it does have a chance to converge conditionally, and that would be by the alternating series test. So if it diverges the absolute value, then you have to go to the alternating series test. Remember, that was the first one, limit as n goes to infinity of a sub n has to be 0. So now if you have to go to your table for this, remember, we doctored it up. We said look at the limit first, and then the a sub k is greater than or equal to a sub k plus 1. So first calculate the limit as n goes to infinity, 1 over n to the 2/3. By inspection, you could say that's 0, or 1 over infinity to the 2/3, or 1 over infinity is 0. Passes the first condition for convergence of an alternating series. And now we have to show a sub k is greater than or equal to a sub k plus 1 for all values of k. And a sub k is just a k and 1 over n to the 2/3. Kn for n, 1 over k to the 2/3. A sub k plus 1, a k plus 1 n for n, 1 over k plus 1 to the 2/3. Okay, which way does the inequality point? Well, denominator on the left always less than denominator on the right, so reciprocal would be greater than. So then it passes the second condition for convergence of an alternating series. So here's how we have to finish excuse me, this one up. So by the alternating series test, this given series converges, but then by definition, so you do have to make these final statements. By definition, remember, we had this definition: if the sum of the absolute value diverged, which it did, that's what happened here, but the sum of the a sub n converges, and it did, and that was by the alternating series test, so we noted that as well, then we can say that the series converges conditionally. So then by definition, the sum as n goes from 1 to infinity. I'm going to recopy the given series, but that this converges conditionally. Okay, so final example. Again, start the same way. Sum of the absolute value of the a sub n. Sum and goes from 1 to infinity. Negative 1 to the nth. Absolute value, that is. Negative 1 to the nth. 2n cubed plus 1 over 3n cubed plus 1 gives us the sum as n goes from 1 to infinity of drop the absolute value and drop the alternating factor of negative 1 to the nth. Okay, so now we have to decide, kind of like the second example, what type of test do we use? Well, so you have to just choose a test to use. And this one, don't ever forget about the first test we've ever used. And whenever you see a ratio of two polynomials like this, you might want to try the nth term test. And that just says to take the limit as n goes to infinity of a sub n, which in this case would be the limit as n goes to infinity of 2n cubed plus 1 over 3n cubed plus 1, which by inspection, hopefully, we've seen this enough. If we have the limit as n goes to infinity of a ratio of two polynomials and the degrees are equal, that limit is just going to be the ratio of the leading coefficients, which is 2/3. Look at the nth term test. That was the first test we talked about. And it says if diverges, if you take the limit, it's not 0. It's obviously not 0. So therefore, it diverges. So then you might say, okay, it has a chance to converge by the alternating series test. But by the alternating series test, the first condition that we checked is basically the nth term test. And it's not 0, so we say it diverges. So therefore we could say that our series, because it diverged both ways, absolute value and alternating, then we could say that our series also diverges. Okay, so that's it for topic 9, and we'll come back when you're ready for topic 10.